Today it's a much nicer occasion because I got the pleasure to introduce my all-time friend and colleague, Robert Milson. So, I mean, you all know Rob's work on exceptional orthogonal polynomials. Maybe you don't know that he's also many other contributions in other fields of mathematics, like general relativity, differential geometry, and actually he did his bachelor's in computer science. So, he's an all-round mathematician. It's really been a pleasure to work with him for the last 20 years. So I think today he's going to give us a talk on review on exceptional polynomials, but also some very recent new material that probably he's going to share with us. So Robert, the floor is yours.
Thank you also to the organizers for inviting me to give a presentation at this 2022 iteration of OPSFA. It's always a pleasure to participate in these meetings and to interact with so many friends and colleagues, even in this virtual format. Still, it's better than nothing. So I guess we should all try to be thankful. So listen, I realize that it's evening for many of you, so thanks for attending the talk despite the late hour. I really do appreciate it. I guess that's one of the corollaries and consequences of this, the ability to do things virtually. Yeah, so my presentation is going to be a survey talk on the subject of exceptional orthogonal polynomials, and my apologies to those of you who have seen various versions of similar talks in the past. As David said, the last third of my presentation will be devoted to some new results, so please stick around. There will be some new ideas. All right, so the talk will be organized into three parts. So part one will be a more or less gentle introduction to the idea of exceptional orthogonal polynomials. We've heard them mentioned in one or two presentations, previous presentations at this meeting. So I'll try to give a motivation for where these things came from. Part two will be a quick survey of some essential aspects of the theory and history of exceptional orthogonal polynomials. And part three will be devoted to some new results on exceptional polynomials that depend on an arbitrary number of continuous parameters. All right, so let's go. Right, so classical orthogonal polynomials. Probably everybody here is familiar about them. They're eigenpolynomial solutions of a differential expression that looks like this. Bachner showed that if such an expression has eigenpolynomial of every degree, then this polynomial P has to be of degree 2 or less, Q has to be degree 1 or less, and R has to be a constant. And many people realized that by filtering this observation carefully, you should be able to arrive at the well-known families of Hermite, Laguerre, and Jacobi polynomials. These are the three families of classical orthogonal polynomials. And indeed, this filtration was carefully done by Leski, who showed that indeed Bachner's observation does lead to the three well-known families. Of course, applications are ubiquitous. I decided to focus on some applications in quantum physics. There's many other applications. So, for example, where it talks about electrostatics and interpolation. So here you see some pictures involving spherical harmonics, which are given in terms of Jacobi polynomials, and eigenfunctions of the harmonic oscillator, which are given in terms of Hermite polynomials. So yeah, so the applications are quite important. Right, so a classical theme. So here's Bachner's 1929 papers. I think it's only like 2 pages long, and literally he proves this very obvious result, that if you have an expression like this, assume that there's an eigenpolynomial of every degree, then necessarily P0 will be degree 2 or less, P1 will be degree 1 or less, and P2 will have to be a constant. And he said that from this very simple observation, it's a very easy task to describe the set of all. And then here's the 1962 paper by Peter Leski, who essentially took Bachner's observation, filtered the various possibilities carefully, and again, and rigorously showed that, like, if you assume that you have a positive definite inner product, that up to, I think it's affine transformations, the only things that you get are polynomials of Hermite, Laguerre, and Jacobi. And then Leski says this funny thing. In conclusion, we state that the classical orthogonal polynomials are the only orthogonal polynomials which are solutions of differential equations of Sturm-Liouville type. In retrospect, we should say, yes, that may be true, but it's only true because certain assumptions were made. So what were the key assumption that I'd like to highlight? It's this assumption right here, that there's polynomials of all grada, of all degrees, right? So this seems like a very natural assumption. Why would you not want to make that assumption? Why would you want to have a family of polynomials which don't include all degrees? But nonetheless, that is an important assumption. So yes, but only provided you have this assumption. All right, so let's see what happens if we allow ourselves to relax that assumption. So here's the Hermite, well-known Hermite differential. It has eigenpolynomial, it has polynomial solutions, which are the Hermite polynomials, which you can easily give using the Rodriguez formula. Now let's do this very strange thing. Let's take the Hermite differential equation and let's throw in this rational modification. Well, it's a second order eigenvalue relation, but seems a little bit random. This second order differential expression does have eigenpolynomials, and in fact, it has eigenpolynomials of all degrees except for 1 and 2. It couldn't possibly have eigenpolynomials of all degrees because that would violate Bachner's observation. But there are eigenpolynomials, right? Because Bachner tells us that the coefficient of y prime has to be a polynomial of degree 1 or less, and this is a rational function. Yes, so here's an example of second order differential expression with eigenpolynomials, but with missing degree. Strange, and it seems like a modification of the classical Hermites by adding these extras. All right, so at this point, if you have never seen this before, you should probably ask yourself 3 different questions. Here's the first question: why do we call these exceptional polynomials? Well, we call them exceptional polynomials because there's some missing degrees. There's some exceptional degrees. And in fact, look at the formula I gave you. And what I want you to do is I want you to convince yourself that this formula doesn't even make sense if we take n to be either 1 or 2. Why? Because if you put an n equals 1 or 2, you'll get expressions that involve classical Hermite polynomials degrees -1, -2, and -3, as you see below. So I just asked Mathematica to calculate the polynomials using this formula, and you see that degrees 1 and 2 doesn't make any sense because you're asked to take linear combination of classical polynomials that don't exist. So here's your second question: how in the world can there be a polynomial solution? Look, we have a rational coefficient in the world. Can you put a polynomial into this, substitute a polynomial into this expression, and have any hope of obtaining a 0? All right. So again, I'll ask Mathematica to help us out here. So I've coded up a rational modification of the Hermite differential equation. I coded up, then I just stuffed the this expression into this differential expression, but I asked Mathematica not to simplify. And so here's what you see. And here's the crazy thing, right? There's some, you're combining polynomials, and then there's a rational thing. And nonetheless, when I ask things to simplify, some strange miracle happens, there's a bunch of cancellation, and in fact, everything goes away and turns into 0. Very strange. So at the least, in order to have this cancellation, we must be able, derivative of this h hat has to be divisible by 1 plus 2x squared. Because if that doesn't happen, then the answer cannot possibly be 0. And in fact, that's an exercise. Actually, with a little bit of fortitude, you can actually use like the 3-term recurrence relation to show that if you take this expression and calculate its derivative, that derivative will always be divisible by 1 plus 2x squared. And with even a bit more effort, you can actually convince yourself that what Mathematica is showing you is valid. That not only will this cancellation happen, but in the end, everything will cancel each other out. And so yes, it seems crazy, but yeah, you can have differential expressions with rational coefficients that have eigenpolynomials. And in fact, lots of them. Right. And the third question is like, why do we call these polynomials not just exceptional, but also orthogonal? We know that the classical Hermite polynomials are orthogonal. So why are these h hats also orthogonal? Here's the classical orthogonality relation. It's orthogonality with respect to this weight. And so what I claim is that these h hats, this polynomial family with 2 missing degrees, is also orthogonal, provided we modify the classical weight by including this mysterious 1 plus 2x squared in the denominator with a double multiplicity. And then not only do we get orthogonality, we get also another indication that we can't possibly have hats with n of 1 or 2, because if we did, norm formula would involve division by 0. So if you believe this orthogonality story and you calculate the formula for the norms, you see once again that degrees 1 or 2 have to be missing, because if they weren't, you'd be asked to divide by 0. Orthogonality come from? It came from actually the second order differential equation, because whenever you have a second order differential expression, what you can do is you can put it into symmetric Sturm-Liouville form, which I do over here, and you multiply it by a certain function, which you calculate by solving the Pearson equation. And then you put things into symmetric Sturm-Liouville form, and then the weight basically you can find sitting on the right hand side. Okay. Yeah, so the weight came from the differential equation. So as soon as we know that they're eigenpolynomials of a second order differential equation, they have to be at least formally orthogonal with respect to something. So what's the story so far? Well, that bold claim that it's easy to find all Sturm-Liouville problems with polynomial solutions may have been a little bit overplayed. And in fact, classical orthogonal polynomials are just a subclass of Sturm-Liouville problems with polynomial eigenfunctions. So you might say, well, maybe that 1 + 2x squared example you just showed us is somehow a rare oddity. It's not. It's not an oddity at all. In fact, it's the classical orthogonal polynomials that are the oddity. There's a whole universe of Sturm-Liouville problems with polynomial eigenfunctions, and classical polynomials only form like a tiny little sliver of So think of classical orthogonal polynomials as a tasty cheese that you can use for applications, and exceptional orthogonal polynomials, it's more or less the same cheese. They share many of the same properties, except that maybe your cheese has holes now. And those holes are not necessarily a bad thing, because they give you some interesting properties and interesting phenomena. Finally, maybe we should modify that observation by Bachner and Leski by saying, well, maybe it is true we can describe all Sturm-Liouville problems with polynomial eigenfunctions, but we have to allow families of polynomials with missing degrees. If we get rid of that assumption that all degrees have to be present, can we still claim that we understand all Sturm-Liouville problems with eigenpolynomials? The answer is yes, but you still have to make an assumption, and an assumption is that there must only be a finitely missing degrees missing. And people always ask me, well, are there examples with infinitely many missing degrees? And I say, I don't know one way or the other. So let me forestall that question. So basically, what you have to do is we have to revise Bachner's and Leski's claim, say that yes, in principle, we do know all Sturm-Liouville problems of polynomial type, but we have to allow for the possibility of a finite number of missing. All right, so let's turn to part 2. What I'll do is I'll give you a little bit of a history of exceptional orthogonal polynomials. Then I'll mention a couple of fundamental theorems, like a couple of structure theorems. And then there's a few other topics that I've talked about, but I've just decided to focus on one of them. I'll tell you a little bit about the zeros and asymptotics of exceptional orthogonal polynomials. So the terminology of exceptional orthogonal polynomials was introduced in a paper written with David and Nikki Cameron, who's somewhere in Montreal as well, and back in 2009. And what we did is we said, okay, let's try to find some orthogonal polynomials that are solutions of a second order differential equations, but let's just assume that our polynomial sequence starts with degree 1, this notion of a KOPS, right? And what we did is we essentially classified all eigenpolynomials that begin with degree 1, all families that are solutions of a second order equations that are missing degree 0. And in fact, we proved that this classification is complete. So we came up with these except x1 and x2 Jacobian Laguerre polynomials. That's where the word exceptional got started. And the whole idea of looking for such families systematically came from that paper. But 2009 was not the first appearance of exceptional polynomials. They were there before. It's just that people didn't think of them as some kind of a specific phenomenon. In fact, the earliest reference I know of orthogonal polynomials, eigenpolynomials with missing degrees, is this 1992 paper by these Russian physicists that introduced these, that studied, I guess we would call it an exactly solvable Hamiltonian with this potential. And they noticed that the eigenfunctions are given in terms of these funny polynomials. But it was a curiosity they didn't study in principle. And in fact, almost quite a bit later in 2013, so I guess 20 years later, we saw that these polynomials introduced by Dubois-Williamsky and Kulagin are just an example of what we now call exceptional Hermite polynomials. Okay, so the Ilyansky-Dubois-Kulagin polynomials, you can think of them as just the simplest example of exceptional Hermite polynomials. And in fact, we saw them earlier. These H hats that I started the talk with, those are precisely the exceptional Hermite polynomials in that Dubois-Williamsky-Kulagin paper. But in this paper with David and Ibrandati, we actually classified all. Another little bit of prehistory, and this is kind of interesting because here's some examples of exceptional polynomials that were actually introduced in an earlier OPSFA. Yeah, this was a talk. This was a paper by Alexei Zhdanov and a co-author, which was also presented at an OPSFA, also dedicated to Richard Askey, but again, quite a long time ago. And so what they did was also very interesting, is they actually started apply Christoffel and Geronimus transformations to discrete orthogonal polynomials, and then by doing a certain duality, basically flipping the index and the variable, they constructed these other discrete orthogonal polynomials that were eigenfunctions of a discrete operator. I also noticed that some degrees were missing. Yeah, there's a Q0 of degree 1, a Q0 of degree 3, 4, and 5. Alexei and Katsana noted the connection to the Dubois-Williamsky-Kulagin paper, and they just left it at that. They didn't continue on to investigate it as a phenomenon. Again, many years later, Antonio Duran actually recovered the Alexei's construction and built a beautiful theory out of it. What Antonio Duran showed, that if you now consider the game, if you now start looking for exceptional orthogonal polynomials in the discrete setting, that is to say eigenpolynomials of a second order difference equation, that the class you obtain is actually dual to the class of discrete Kroll orthogonal polynomials. So it's a beautiful duality theory developed by Antonio Duran. I will not be talking about discrete orthogonal polynomials in this talk, but again, it's a very compelling story, and it generalizes what was given by Alexei and Oksana. All right, since then, there's been a lot of work on XOPs with many different applications. So I've listed some topics, color-coded some topics, and then I just listed a bunch of people that have written on those topics. If there's people missing from that list, my apologies. I tried to be systematic, but there's probably missing. And also, many of these people should be multicolored because people have contributed. Many of these authors have contributed in more than one of these areas. Okay. For example, a talk devoted to the connection of exception XOPs and superintegrability. So let's come back to our fundamental question. So really, the question that Bachner and Lesky posed was interesting. Let's try to find all-Sturm-Liouville problems with polynomial eigenfunctions. So is it correct to say that exceptional orthogonal polynomials with the classical orthogonal polynomials included as a trivial subclass are the only orthogonal polynomials which are solutions of a differential equation of a Sturm-Liouville type? So that's the proverbial million-dollar question. And now we can say the answer is yes, provided we assume that only finitely many degrees are missing. So this is actually a theorem. So let me go ahead and present that theorem to you. Actually, I'll present two theorems. But the conclusion is that yes, in principle, we now can characterize all Sturm-Liouville problems with eigenpolynomials, provided we make this one finite degree assumption. All right, so what is kind of the key idea that allows us to get at this fundamental observation? And the fundamental idea is that really, when you look at a family, what you're doing is you're actually looking at a classical family, but conjugated by a change of basis. So let's look again at the example we started with, where we have this exceptional operator and this classical operator. Classical HNs are the eigenfunctions of the classical operator, and the HN hats are the eigenfunctions of that. And this HN hat is given as this linear combination of classical Hermite polynomials. Well, the key observation is to note that this formula, you can give another formula for H hat in terms of a differential operator. Okay, it's a little exercise to show that this HN hat is actually given by the Wronskian of HN with H1 and H2, and then divided by n minus 1 and n minus 2. Once you have this A, this is like a change of basis. matrix. Because you see, you can also show that t into hat are related by this intertwining relation, which formally looks like a change of basis formula. So now we kind of have a hope, because we know that the hope is that we can construct all exceptional polynomials by doing a similar conjugation. The careful treatment of this involved Darboux transformation, but let's just call this dressing. Let's call the transition from T. So in a 2013 paper with Nikki and David, we made the conjecture that every exceptional T hat can be obtained from a classical T by some kind of a dressing differential operator. Okay. And this denominator polynomial, which in our example is this 1 plus 2x squared, which seems to play such an important role, is actually the leading coefficient of this A, just like here. So in the intervening time, this conjecture has been promoted to a theorem. So let me tell you a little bit about that. All right, so before I state the theorem, just a little bit of terminology and a few definitions. So given any second order differential expression, let's just collect all the eigenpolynomials that this differential expression may or may not possess, and let's just count the degrees of all those eigenpolynomials. Generically, this will be the empty set. But in some happy circumstances, particularly if p is of degree 2 or less, q is of degree 1 or less, or r is less, this I of t will be a large set. And let's define an exceptional operator to be such a differential expression where this degree sequence contains all but a finite number of exceptional degrees. And then we'll say exceptional polynomials are eigenpolynomials of such an exceptional. And then we'll promote these exceptional polynomials to exceptional orthogonal polynomials. The O is for orthogonal. We can actually find a positive definite inner product with respect to which they're orthogonal. Now, if you put this second order expression into a Sturm-Liouville form, there will be a weight with respect to which the polynomials are formally orthogonal. But what we want to do is we want actually to filter things to make sure that our inner product is not just formal, but it's actually positive definite. And if you do, then we speak of exceptional orthogonal polynomial. All right. And then in classical operating polynomials will simply be the subclass where IT is all event. This typo is going to persist for the rest of the slides. Okay. And Bachner's theorem simply says that if there's no missing degrees, then you can say this about their coefficients. And as a Lesky corollary, then we have the classical orthogonal polynomials of Hermite, Laguerre, and Jacobi, which again are obtained here by this filtration process. So reminder, if you allow missing degrees, then Bachner's theorem doesn't apply, and there are novel exceptional orthogonal polynomials that are solutions of second order eigenvalue problems. And now the question is, okay, that's wonderful. So let's try to classify all these things. It's one thing to be able to characterize something, but if you want to say that we found all Sturm-Liouville problems with eigenpolynomials, we'd like to make a list. We'd like to make a classification. Here's the first step to that classification. This is from a paper in 2018. I guess it was published in 2021, but the preprint first started circulating in 2018 with David and Maria Ángeles García Ferrero. And what we were able to prove is that just like in the classic case, there are only 3 classes of exceptional orthogonal polynomials, which belong to either the Hermite, the Laguerre, the Jacobi class. And the corresponding exceptional families are determined by this polynomial, which I'll call tau. Right. So in the previous example, tau was 1 plus 2x squared, whose degree is exactly the number of exceptional degrees. So remember, in the examples we showed earlier, tau was 1 plus 2x squared. We were missing 1 and 2. Whatever your exceptional orthogonal polynomial family, there will be this polynomial tau, is the number of missing degrees. Even though we speak of exceptional orthogonal polynomials, often it's more convenient to take these exceptional polynomials and to divide them by tau, and to make these families of rational functions with a common denominator. And this has a slight technical advantage. And one of the technical advantages is that if this really is a family of exceptional orthogonal polynomials, then these rational functions are eigenfunctions of these modifications of the classical Hermite and Jacobi differential equations, which just involve this little rational modification. Now, if you conjugate these expressions by tau, if you do a gauge transformation, you can actually find a second order differential expression for which the polynomials are eigenfunctions, but it has a slightly more complicated form. So that's one advantage of working with these rational functions is their differential equations that are slightly tidier. The other advantage is that if you look at these rational functions, then they're all orthogonal with respect to these classical weights. These are the orthogonality weights for the pi's. Now, if you want to talk about the orthogonalities of the actual polynomials, then you have to take these classical weights and you have to by the square of the tau, which is why we often call tau the denominator polynomial, even though it has some, there's a reason why I use the symbol tau. So really what this theorem, which we call generalized Bochner's theorem, because it really tells you something about the coefficients of these operators, allows you to do, it says that, okay, so if you want to get your hands on all exceptional orthogonal polynomials, you first have to classify all suitable taus. You can't just pick a tau at random. Sure, you can pick a tau at random, stick it in one of these formulas, but you're not going to get eigenpolynomials. Only very, very special taus will give you eigenpolynomials. And then we were also able to prove this fundamental theorem that yes, indeed, the dressing conjecture can be promoted to a theorem, namely for every exceptional t hat, there does exist a classical t and a dressing operator A such that t hat is the dressing of a classical t. About the proof, it's long and complicated, but at least we're well on the way to this eventual classification of exceptional orthogonal polynomials. So now we've moved things from classifying taus to classifying these intertwiners A, or these dressing operators A. And for various reasons, that's actually a more tractable reason, because usually this A's can be given in terms of Wronskian. And so the only thing you need to do is you need to figure out, so A of Y is the Wronskian of a bunch of things in Y. You multiply it or divide it by something. So the only thing you need to know is what are the things you need to put in the Wronskian. And what you need to put in the Wronskian are somehow the eigenfunctions, certain eigenfunctions of the classical polynomial. So this theorem does make a classification within reach. All right, and the last thing I want to do in part 2 is tell you a little bit about the zeros of these exceptional orthogonal polynomials. All right, so let's look at a picture. So here are the classical polynomials of degrees 0 through 4. And of course, you see the usual interlacing phenomena. And now let me plot the exceptional degrees Hermite polynomials from the example we were looking before, the thing with the missing degrees 1 and 2. And what you notice is that they're kind of similar, because you still have the interlacing property, and you still have if you count the number of real zeros, it doesn't match the number of degrees, because the number of real zeros is 0, 1, 2, 3, and 4. It has to be, because these are the solutions of the Sturm-Liouville problems. So the Sturm oscillation theorem applies. So H3 has 1 real zero, H4 has 2 real zeros. So the question is, where are the extra zeros? What we have to say is that we have to say the exceptional orthogonal polynomials have 2 types of zeros. There's the regular zeros that lie in the support of the measure. We saw them earlier, so in this case, there would be real zeros. And they interlace and follow the same asymptotics as the zeros of classical orthogonal polynomials. And then there will be these extra zeros, right, that lie outside the support of the measure. And for fixed codimension m and large degree n, they converge to the zeros of this denominator polynomial tau. So we were working together with Arno Eulers, and we were able to prove this for the class of exceptional Hermite polynomials. And so here's some pictures. So what I did is I plotted the zeros. In red are the zeros of H hat, and in blue are the zeros of the classical HNs and of this denominator polynomial 1 tau, okay, which which is just the zeros of 1 plus 2x squared. So these exceptional zeros, they're imaginary, yeah, and the regular zeros, they're real. And so look at these asymptotics. Look at what it says. The regular zeros seem to converge to, or at least have the asymptotic behavior of classical Hermite zeros. And the exceptional zeros, they converge to the zeros of 1 plus 2x squared, which are purely imaginary in this case. And what we in Arno proved is we proved that in almost every asymptotic sense, in almost every sense you can imagine, the asymptotics of the regular exceptional zeros match the asymptotics of counterparts. So here, for example, if you count the density of the zeros, you recover the usual Wigner circle. So let's talk about some new stuff. Let's talk about part 3. When you work with classical orthogonal polynomials, you know very well that classical Hermite polynomials have no extra parameters. Laguerres have 1 real continuous parameters, and Jacobi classical polynomials have 2 continuous parameters. Well, now let me show you an example. Okay, and previous to this work, when people constructed exceptional orthogonal polynomials, what they would actually do is they would stuff Wronskians with finite lists of eigenpolynomials of a classical operator. And so what you would get is you would get families indexed by an arbitrary number of discrete parameters. Let me show you examples where you can construct families of orthogonal polynomials that are eigenfunctions of a Stubble problem with an arbitrary number of continuous parameters. In some sense, actually, there's infinitely many parameters, but let me explain. All right, so as I said, up-to-date families of exceptional orthogonal polynomials have been indexed by a finite number of discrete parameters. So for example, this is how you construct exceptional Hermite polynomials. You stuff a Wronskian with a finite list of classical Hermites, freeze these indices. Maybe I should put here, because there's a depends on what you mean by n over here, but usually you have to include a degree shift. So this is not quite right. Usually like a certain degree shift that happens here, but it's not important. The point here is that the family is indexed by a finite number of discrete variables. So they're newly discovered families of exceptional orthogonal polynomials with an arbitrary number of continuous parameters. These parameters serve to describe isospectral deformations of classical and exceptional Jacobi. The price you have to pay is that these deformations that you're performing, they have to be done to families of Jacobi operators with integral of alpha and beta. So alpha and beta, which usually are continuous, now have to be made into discrete parameters. All right, let me show you just a little bit of history. So the first example of this phenomenon was discovered by Yves Grandati and Christian Ken in 2015, who basically wrote down a bunch of one-parameter families. And then in 21, working together with Marie-Angeles and David, we wrote down isospectral deformations of classical Legendre operators. And we saw that you could have as many deformation parameters as you wanted. And then later this year, Antonio Duran showed that it is possible now to deform not only classical orthogonal operators, but you can also do deformations of exceptional operators. All right, so let me just show you some examples. So, the general Bachner theorem that was proved together with Marie-Angeles and David tells us that if you're going to have an exceptional Legendre polynomial, it has to be the solution of a differential equation that looks like this. Okay. If tau is equal to 1, then you just recover the usual Legendre differential equation. Right? So if there are any exceptional Legendre polynomials, they have to look like this. The only question is, what I'm going to show you is I'm going to show you how to construct a tau, which in principle depends on infinitely many parameters. Although in order to get polynomials, you have to set almost all but a finite number of these parameters to 0, and such that when all the parameters are 0, you just recover the classical Legendre operators. Okay? And under these parameters, what happens is you have the norm evolution of these pi n's. What are the pi n's? They're just the pi hats divided by tau. Okay? So that's the idea. And now let me show you some plots. Okay? So here you see a plot of classical Legendre polynomials. And now what I'm going to do is I'm just going to set T1, T2, T3, T4 to 0 and only play around with T0. Then what you're going to see is you're going to see that the norm, because remember the norm of the pi's is just the usual Legendre weighted inner product. Okay? So it's just the usual norm square. You see is that the deformation, it moves the other eigenpolynomials without changing their norm squared, but it evaporates the norm of the 0th one. Okay, so here's another example. So here's an example where we have 3 parameters. So now T2, T3, T4 are allowed to vary. All the other T's are set to 0. And again, we start out with the classical Legendre polynomials. And then again, we see the usual thing, the norm squareds of the dashed lines, they evaporate to 0. All the other eigenpolynomials, they get deformed, but their norm squareds. This is now the formulas for these are all quite explicit. But before I show you some explicit example, let me just explain to you roughly where these deformations came from. We were able to do these constructions because we started employing something called confluent Darboux transformation for short. But since I didn't talk about Darboux transformations in the talk, just think of them as confluent dressings. Okay, and let me tell you what's so confluent about these dressings. All right, so let's go back to our intertwining relation over here. This intertwining relation, you very quickly realize that the kernel of A has to be an invariant subspace of T, right? Because if A of F is 0, will also be in the kernel of A. T preserves the kernel of A. If A is a finite order differential operator, it's going to have a finite kernel, which means that T restricted to the kernel of A, is a finite dimensional linear transformation. And the eigenvectors of this restriction are called the seed eigenfunctions. And in fact, they're the things you stuff into the Wronskian. There's a proportionality factor that you usually have to add, but let's not talk about that. Okay. And generically, when, at least in the examples that people knew up to then, when you did this construction, all of these phi's had different eigenvalues. In other words, this finite dimensional transformation was diagonalizable. So what we said is, like, is it possible to play this game, but to find examples where you have repeated eigenvalues, confluent eigenvalues, where this transformation has some kind of a Jordan blot? And indeed, it turns out to be possible to do this. Okay, and know from the theory of integrable systems is that when you do this confluent dressing, you introduce continuous parameters. In fact, that's how you dress KDV, right? That's how you add the evolution parameters of KDVs, by these confluent dressings. Okay, so what we actually are able to show is that we were able to confluently dress classical Jacobi operators, but provided the Jacobi parameters were took integral values. All right, so that's the idea in a nutshell. Okay, let me show you some explicit formulas. This one parameter exceptional Legendre polynomials, and these are isospectral deformations of the classical Legendre operator. Okay, everything is very, very explicit. Remember, once I tell you what the tau function is, so once you have the right tau, this is the operator. All right, so how are we going to construct it? Well, the first thing we're going to do is we're going to look at the incomplete norms of classical Legendre operators, right? If x here is 1, you're just going to get you're either going to get a 0 or the norm squared of the classical Legendre operators. Okay, and I'm simply going to take this as my tau function. Then this is my p hat. See, everything's very explicit. And again, for many reasons, it's easier to work with this rational function, where I take my exceptional polynomial p hat and divide it by the tau, and then you get this very nice expression. And you can see that it's kind of a modification of pi. By the way, these p hats, they're not labeled with degree. K here is not degree. You see, when you're labeling exceptional polynomials, there's two very natural ways to do it. Number one, you could label them by the degree of the polynomial, but another perfectly natural way to do it is to label it by the number of regular zeros, because those exceptional zeros are somehow not visible from the point of view of Sturm-Liouville theory. So here, when we, the nomenclature for exceptional Legendre polynomials, this label K refers to the number of regular zeros, not the degree of the polynomial. The degree of this pi hat is actually usually much, much larger than K. In fact, it's usually K plus the number of missing degrees, plus the degree of this. Well, the nice thing is that, and again, this is all a claim, is that these deformed pi hats, they really are a deformation of the classical Legendre orthogonality, right? If T is 0, you just recover the usual Legendre orthogonality, and if not, then you have a deformation. And moreover, everything is very good. This rational function has no poles in the domain of orthogonality, precisely when this norm is positive. So in fact, we don't have to do this regularity filtration. As long as this expression is positive, well, actually, this inequality is the regularity filtration, right? Then this integral is actually, filtration is very easy to see. It's just the requirement that the norms of our exceptional objects be positive. All right, so let's look at a two-parameter example. And I could have written these explicitly, but it's actually nicer to write them like this. So again, Rij's are incomplete inner products of classical Legendre polynomials. Now our tau function now is going to be this 2x2 determinant, deformation parameters. And our exceptional polynomial is now this 3x3 determinant. Rational function, which is the exceptional polynomial divided by tau, you see that it's some kind of a modification of the classical Legendre operator. And again, you see that the orthogonal relation shows you that what you're doing is you're messing around with the norms of pk1 and pk2. Okay, and the reason why I showed you this is that this really looks a lot like the determinant formula for a two-soliton. And the reason why it looks like a two-soliton formula is because really what we're doing here is we're more or less playing the same game you play when you when you obtain KdV solitons, which is where you address the trivial Hamiltonian, except now we don't start with a trivial background. What we do now is we address the so-called Darboux partial Teller. So it's a certain infinite square well potential. So really that's where you can think, if you prefer to think of in terms of Schrodinger operators, all of these new exceptional deformations, they're coming by playing the addressing game, but not with a vacuum background. But wait, this Darboux partial Teller potential is equivalent by gauge and transformation and diffeomorphism to the usual. The difference is that the eigenfunctions of the Schrodinger operator have this little prefactor over here, and you have to use it, make a change of variable. Okay, so the news is that if A and B here are integral are natural numbers, you can isospectrally deform these things and have the wave functions still be given in terms of polynomials. Again, you form the incomplete inner products, except now instead of just the Legendre weight, you have the weight corresponding to an arbitrary A and B. And otherwise, you build things in the same way. You build a tau function using this determinant of this matrix. You build the p hat using the determinant of this matrix, and you build pi in the same way. And in the end, you get an isospectral deformation of the Darboux partial Teller potential. And how do I know and that this really are isospectral deformations? Well, because you see, you can obtain all of these formulas in terms of something called the Gelfand-Levitin-Marchenko. When you do inverse scattering, you can describe the dressing as a solution of this integral differential equation called the Gelfand-Levitin-Marchenko equation. And then if you limit yourself to the soliton regime, you can then rewrite the solution of that integral equation. And that's exactly what's going on over here. Spare me the details, I don't have time. Instead, I'll show you something. Right, so here's some 3-parameter example. So here's some families of orthogonal polynomials that are eigenfunctions of H2 problems, but now they depend on 3 continuous parameter. Why 3? Well, because 3 is bigger than 2. I could have also done a 4 family, 4 parameters, 5 parameters, as many parameters as you want. So here, again, I'm going to be playing around. I'm going to take alpha and beta to be 1. I'm going to be playing around with the norms of psi 0, psi 1, and psi 2. All the other norms I'm going to leave alone. And now I'm looking at things in the Schrodinger gauge. Yeah? So the thick blue line here, that's the Darboux partial Teller potential, and everything else, those are the eigenfunctions. And what you see there is the classical picture. As I drive my deformation parameters T0, T1, T2 ever higher and higher, we see what we expect to see. The norms of the first 3 eigenfunctions evaporate, and the other eigenfunctions slide around. And really, the way to do this is to create this like big hole near the end. By the way, what I'm doing here is, in order to talk about norms, you have to impose some kind of normalization, and the normalization is imposed at the right endpoint. All right, so here's another example. So this time what I do is I take my deformation parameters and I drive T1 and T2 to infinity so that I evaporate the norms of psi 1 and psi 2. But what I do is I drive the deformation parameter T0 in such a way that I blow up the norm of psi of the 0th eigenfunction. And so this is what you get. Is the norm of psi 0 blowing up, the other norms shrink away, and all the other eigenfunctions, they just slide around a bit. And you see that in order to do that, you need to create like a hole over here and a hole over here. So you can think of things in terms of a little bit of quantum mechanics. All right, so here's some concluding remarks and questions. Right, so classical and exceptional orthogonal polynomials, maybe classical orthogonal polynomials are just really, really classical. Okay, they're the old exceptional polynomials, and And introducing exceptional orthogonal polynomials is very, very natural. They should have been, they have been invented before. And they're, whenever you talk about classical orthogonal polynomials, you should also be talking about exceptional orthogonal polynomials, because you're not really changing much. These two classes share many of the same properties. About recurrence relation, that's a very interesting story. It involves bispectrality and integrable systems. Again, just roughly speaking, we ditched the three-term recurrence relation for an algebra of higher order recurrence relations. So again, sorry, I probably don't have time to talk about this now, but it is a very interesting topic. There has been some work on application of things to approximation, interpolation. I think Andrea Horvath has done some work on an exceptional version of the Fekete problem that we talked about earlier, but still there's very, very little in this area. So for example, nobody has really studied like the electrostatic interpretation of the exceptional orthogonal polynomials. I think at this point, we're very close to a complete classification. Maybe I shouldn't sell the rug before we kill the bear, but in some sense, it seems like these class of deformed orthogonal polynomials with continuous parameters were the missing piece. So now probably we have the full classification at hand. It just remains to write it down. The exceptional story is very much worth telling. That Antonio Duran calls this the generalized ASCII scheme, and you have this beautiful connection with exceptional Kral polynomials. Sarah Post told us earlier about these examples of superintegrable systems constructed on the basis of exceptional Jacobi operators and polynomials. Well, now the question is like, is it possible to construct superintegrable potentials with an arbitrary number of continuous parameters? I say that the answer is yes, because I mean, you still have exceptional in Jacobi polynomials, except now they have an infinite number of continuous parameters. So surely the construction that worked before should work again. So that remains an open question to that suggestion. And that's it for my talk. Thanks for your attention. It's time for me to.
Okay, thank you very much, Rob, for this very nice lecture. Now it's time for questions.
Yeah, I have a question. Yes. Okay. You showed a formula for the equilibrium measure for the exceptional Hermite.
I think I showed any equilibrium measures. Huh? Oh, no, you mean
it's the arc sine. Yeah.
Oh, you mean the Laguerre semicircle law?
So presumably you can prove that the largest zero behaves like square root 2n or 2n plus 1. And is the error term, does it involve the zeros of the area function, or?
We didn't touch that in the paper with Arno. I'm going to guess the answer is yes, because so far every kind of characterization we threw at these exceptional zeros matched their classical counterpart. So I'm going to guess the answer is yes, but Arno and I didn't study the question.
Okay. My other question is, if you look at the graphs of the Laguerre polynomials and you take the modulus of the Laguerre, so instead of the oscillation, now you have these humps.
You mean talking about Jacobis?
No, I'm talking about Laguerre.
I don't think I talked
classical
about
Laguerre.
Okay.
Classical Laguerre.
Okay.
So if you look at these humps, you can prove that they are monotone. Do you know, did you graph? Okay, so I suspect you probably have the same property, but not right from the beginning, because you have complex zeros. So the early part may be different, but I think the later part would be the same.
Yeah, so this is exactly a question in this category. There's many results in the theory of classical orthogonal polynomials, which involve interpretation like max-mins, and the sentiment is that they should carry over to the exceptional world. But other than the work of Andreas Horvath, really nobody has done anything like that.
Yeah, but I think it would be nice to graph these at least for something like Laguerre, and look at these humps and see what happens.
I agree.
Okay, thank you.
Oh, I think Peter Miller has a question.
Yeah, I've got a question. Rob, very nice talk. So my question is probably pretty simple. I just want to check my understanding. But in the Hermite case, exceptional Hermite case, is it right that you can't have an odd number of missing degrees? I mean, do the exceptional zeros have to be in conjugate pairs?
Yes, yeah, because they're all exceptionals. That's right. So the number of exceptional degrees have to be, there has to be an even number of exceptional degrees.
In that case, but I guess in the Jacobi case, you could have real exceptional roots.
Yeah,
that are
I haven't studied the
right?
asymptotics of exceptional Jacobi zeros. So yeah, so like, are they? I don't think you're limited to the possibility of complex zeros. There will also be some zeros that are just outside -1, 1.
Just outside the interval, right? Okay. Anyway, thank you very much. Nice talk.
Yeah, you were supposed to ask me about Lax pairs.
Okay, what about the lax pairs then?
Well, okay, so the thing is, like, when I wrote all these things down, I thought for sure I would be able to write down a lax pair, because I mean, like, to see where this evolution came, and surprisingly I couldn't. Like, so we have this. I mean, like, because it is because you have this isospectrality, so morally there should be a lax pair in the background. Reason maybe it's just I'm dense, or maybe I just not looking at the right things. I tried and I could not write it down. It's an open question to try to express this isospectral deformation of these of the classical Jacobi operators in terms of.
Okay, we've got another question by Jolion de Freitas.
Thank you very much. I thoroughly enjoyed the presentation this evening. It's pretty much past 10 here in the UK. I have a question with regards to the application of this for quantum systems. Have you tried, or do you know of applications where you've applied this, say, to semiconductor quantum systems, where you have 3 or 4 atomic layers, and the way the Hamiltonians and the potential wells behave would seem to be pretty similar to this. Is there any application of this type of system into that?
We have so many results, and it seems like this new variety of special functions and exactly solvable potentials should have some nice application to modeling. There's a few papers on like mass dependent potential, things like this, but again, it's another area which has not at all been explored. Like, also, can you use these exceptional polynomials, for example, to do Gauss, Legendre, Chebyshev type, integration schemes? Maybe yes, maybe no, I don't know, but it's another question that is easy to state, but which nobody has worked on. So the suggestion is yes, because the bigger your toolbox, the more interesting models you can cook up. But it's not much work has been done in this area. Maybe I don't know.
Yeah, I think what's being done at the moment is a lot of different equation type solutions to the electromagnetic equations, and you solve your problems that way. So it's a purely numerical approach, if I'm not mistaken. So it would be interesting to see how these type of analytical solutions, perhaps starting with some very thin, unusual looking potentials, and relate that to some kind of atomic layer structure, and extract from that what is actually happening below at an atomic layer. And there's several fantastic things going on in terms of magnetism, electrostatics, you mentioned there, and there are a host of other photonic type interesting quantum phenomena that's going on at the moment that people are studying experimentally. But in terms of the actual modeling of these things, I suspect that they are far more difficult, and this looks like a solution to that.
Yeah, no disagreement, not at all. It's definitely an area that bears.
We have 2 more questions. So Paco and Manuel. So let's go with Paco.
Yes, thank you very much, Rob, for your presentation. I have 3 questions. The first one is related with a question that I posed in several times. If there are explicit relations between exceptional and classical orthogonal polynomials. To show in the case of Hermite polynomials, where first degree 1 and 2, that you can represent the exceptional Hermite polynomials as a linear combination of hn, hn minus 2, hn minus 4. Essentially means that these polynomial, exceptional polynomials, are quasi-orthogonal with respect to the normal probability. And my question is, this is true for any family of exceptional orthogonal polynomials?
Yes, it is. In fact, we have the explicit formula for the Hermite class in a joint paper with Alex Kasman. And we haven't done it, but I assume the same techniques will also apply to the other two classes. Yeah.
Okay, because I have the flavor that in such a case, Hn hat are orthogonal with respect to some measure, okay? And this measure is related with the fact that you have this kind of quasi-orthogonality of order 4. That means...
But Paco, do you have to assume that all the H hat n is defined for every n?
The second question, you say that exceptional orthogonal polynomials share properties of classical orthogonal polynomials.
Yes.
My question is, there are ratio asymptotics of these exceptional orthogonal polynomials in terms of classical orthogonal polynomials? Because
yes,
we have...
There's some ratio asymptotics in the paper with Arno. And I think Arno and Niels extended this to the class of exceptional Laguerre polynomials, where they also studied ratio asymptotic.
And then my last question is related, following the guideline of Murat, what happens with the exceptional zeros? That means regular zeros behaves in some very good unexpected way, but what happens with the exceptional zeros?
I think Niels and Arno would have a better idea because they studied the asymptotics of the exceptional Laguerres, but I don't remember what the results are.
Yeah, it's similar, if I may, it's similar to what's happening in the case of Hermite, right? What Rob was explaining. They go to the zeros of tau, this extra factor. I mean, this they go into the complex plane after appropriate scaling.
Thank you. Thanks, Arno, for popping in. So we got one last question by Manuel Dominguez in Iglesia. Manuel.
Thank you, Rob. Hi, very good talk. I have a question regarding the original Buckner problem. In the original Buckner problem, apart from the classical families of Hermite, Laguerre, and Jacobi, there are two more polynomial solutions. That are the Bessel family and the so-called Romanovsky polynomials.
Yeah.
So have you tried something?
So there the problem is they don't satisfy the regularity condition. The inner product is not positive definite.
Well, but
Not
they are
positivity.
now in some
Not positivity.
Positivity filter.
But for instance, the Bessel polynomials will be orthogonal with respect to a measure on the unit circle. No? Maybe you can extend some of these ideas apart from positivity. Apart
No, if you let go of the positivity assumption, at least in principle, this hasn't. There's a work by Sasha Veselov and collaborators. I forgot the other two collaborators that showed that the Hermite class, every family of exceptional polynomials is orthogonal. You don't have to apply this what they call the Krein-Adler condition, which assures positivity. Is if you are willing to, there's a very natural way to define an inner product, regardless of whether or not tau has real zeros. The problem is if tau has real zeros, and you write down the weight, the integrals are singular because they have poles. How are you gonna integrate something which has a pole of order 2? Basically, if you just move the counter off of the real line in a fairly this way, you can still define an inner product, and then it works for every tau. And then they showed that they're orthogonal with respect to this inner product, but this inner product is no longer positive definite. It has a finite index. I'm guessing that the same thing will hold for the other families. So yeah, so if you let go I mean, it all depends on how you interpret the term classical orthogonal polynomials. If you want your inner product to be positive definite, then Hermite, Laguerre, and Jacobi is all you're going to get. If you relax that assumption, then of course you get Romanovsky, you get Bessel, and the story is even more interesting in the exceptional world, because then you also get orthogonal, you get Krein space type orthogonality for other families.
Okay, well, I think there are no more questions unless somebody didn't raise their hand. Let's give a big clap to Rob again, and I guess we'll meet back in 20 minutes for the last talk. So thank you, Rob.